All right, let's get into it. You know those physics problems that just make your brain hurt? The ones from books like Irodov? Well, today, we're going to crack one of those wide open. We're tackling the infamous problem 1.68, step by step.
Okay, so here's the problem statement word for word. You see that force, F equals at? That's a huge clue. The force isn't constant, it's changing over time. And then there's that phrase, breaking off the plane. Sounds kind of dramatic, right? But don't sweat it. We're just going to figure out two things: how fast it's going and how far it's gone at the exact moment it lifts into the air.
So, to make sure we don't get lost in the weeds, here's our roadmap. We'll lay out our game plan, dig into the vertical forces, then the horizontal motion, and then bring it all home for the final answer. We'll also cover some common mistakes to watch out for.
Okay, let's talk strategy. Before we even think about writing down an equation, we need a plan of attack. A good strategy is honestly half the battle.
It's a simple four-step process. First, we'll figure out the when, the exact moment of liftoff. We do that by looking at the vertical forces. Then we'll figure out the how it moves horizontally. And last, we'll just plug the when into the how to get our final answers. See? Simple.
All right, step one. Let's focus only on the vertical direction, up and down. This right here, this is the key that unlocks the entire problem. Figuring this out tells us the exact moment that little body says, "See you later" to the plane.
So let's draw our forces. You've got gravity, mg, pulling it down. And fighting against that, you've got two upward forces. The plane itself pushing up, that's the normal force, n, and the vertical component of our applied force, which is F times sine alpha. As long as the body's on the ground, it's a perfect stalemate. The ups equal the downs. No movement, no vertical acceleration, at least for now.
Now let's talk about that phrase, the break-off condition. This isn't just a casual term. It has a very specific physical meaning. It's the exact instant, the very moment, that the plane is no longer in contact with the body. And what does that mean for our forces? It means the normal force, N, has just gone to zero. Kaput. Gone. And that little fact makes our lives so much easier. If N is zero, look what happens to our equation. All we're left with is the vertical part of our applied force, F sine alpha, perfectly counteracting the weight of the body, mg. It's doing all the work by itself now.
Okay, now remember what the problem told us about our force F. It's not just a number, it's a function of time. F equals a times t. So we can just take that and plug it right into the equation we just found.
And boom, with just a little bit of algebra, we can solve for t. This t isn't just any time, it's the exact time of liftoff. This is a huge step. We've just solved the first major piece of the puzzle. We know when this all goes down.
Okay, so we've got the when. Now let's figure out what's happening horizontally during that time. How fast is this thing moving, and how far did it get?
Switching gears to the x-axis, it's actually simpler here. The only force acting horizontally is just the x component of our main force, which is F times cosine alpha. And according to Newton, that force is what causes the body to accelerate sideways. F equals ma, right?
Okay, stop. Pay very close attention right here. This is the #1 mistake people make on this problem. Since F equals ma, our force is changing with time. That means our acceleration, Wx, is also changing with time. It is not constant. If you treat it like it's constant, you're going to get the wrong answer. This is the big trick of the problem.
So that leads to a pretty important question, doesn't it? If the acceleration isn't constant, how in the world are we supposed to find the velocity? All those simple kinematic equations we learned, they're out the window.
And the answer, my friends, is calculus. When things are changing constantly, we need a tool that can handle that change. And that tool is integration. It's basically a way of adding up an infinite number of tiny little changes to get the total.
So to get our velocity at any given time t, we have to integrate our acceleration function with respect to time. Think of it like this. We're summing up all the tiny little speed boosts it gets, second by second, from the very beginning up until time t.
And once you do that integral, which is a pretty standard one, you end up with this nice little formula for velocity as a function of time. This equation will tell us the velocity at any time t we want.
And guess what? To get the distance, we do the exact same thing again, just one level up. We integrate the velocity function we just found. And that gives us a new formula, this time for the distance traveled at any time t.
Okay, this is it. The final step. We've done all the hard work. We have the specific time of breakoff, and we have our general formulas for velocity and distance. Now, we just put them together.
For part A, the velocity, all we do is take that special time t that we found way back in the beginning and plug it right into our velocity equation. That's it.
And for part B, the distance is the exact same move. Take that break-off time, plug it into our distance equation, and there's our final answer for the second part.
So there you have it. We've solved the problem. But just getting the answer isn't the point, right? The real goal is to understand why it worked and what we can learn from it for the next tough problem.
So let's recap the big takeaways here, the common traps this problem sets. Number one, and this is the big one, variable force means variable acceleration, which means you have to use calculus. Don't even think about using those simple v equals v0 plus at equations. Number two, always break down forces into their x and y components. And finally, remember what breaking off means physically, n equals 0. If you can remember those three things, you'll be in great shape for problems like this.
And just to leave you with a little something to chew on, we found the velocity at the exact moment it lifts off. But what happens a split second after that? It's airborne now? What kind of motion is that? What forces are in play? Think about it. Thanks for joining me on this one.